All right, everybody, 2 o'clock. Welcome back to your favorite class. First things first, I got a new microphone. So those of you that are sort of online, if the sound is weird or something strange is going on, please let me know. Type something into the chat and make sure that you can hear me and that it's clear and everything is good, okay? I did bring my other headset with me today in case this one is a little janky, but I like this one because it gives me one ear where I can listen to the people online and one ear I can listen to the people out in the real world. I feel like a telemarketer, but you know, it is what it is. All right. The meme. Okay, so people like the meme today. It's very Christmas oriented. I'm in the spirit, okay? Right. So a couple of announcements for today. Homework number 1, which is on vector math, was due 1 minute ago. Hopefully you got that in. As you'll see, I try to grade homeworks quickly, usually within 24 hours. And the reason for that is because it's good to get feedback quickly, because it's fresh in your mind, like what you did and how you did the problem. So I like to give feedback as quick as I can. Homework 2 is going to be posted soon, probably tomorrow. That'll probably be due like later in the week next week. And that's because exam number 1 is next Friday. So I'll probably have the homework due maybe Wednesday. And then your first exam for the class is going to be next Friday during the class time. So already coming up pretty quick. A little bit of vector math, 2D particle equilibrium, and 3D particle equilibrium. That's what we're going to have on the test. All right. So there are not any further questions, then I'll just kind of pick it up where we left off with our 2D particle equilibrium. How's the sound? Sound okay online? How's the sound in person? The sound in person is terrible, according to Victor. Okay, so let's sort of refresh ourselves where we left off. Last time we were talking about 2D particle equilibrium, and we'll break that down in just a second here with a little bit more detail, but the idea here is we're looking at do the sum of the forces of a variety of different vectors that act at a particle equals 0. And we were checking that with this kind of crazy looking situation here where we had 4 forces that were acting on a particle. And we saw that if we do sort of go with the tip to tail method and put all these forces together, using the tip to tail method, we would get back to our original location. And so if we're getting back to our original location, then the resultant of all of these forces here, when you add them all together, is going to be 0. And that's what it sort of means to be in equilibrium, is that the resultant of all of the forces that are acting at that particular particle is equal to 0. So here's the example with sort of our tip to tail method, but we also went through a long example to sort of show that this is true and could be true using our vector math. And you know, trying to draw all these forces with a tip to tail method, you probably saw in your homework, kind of annoying, all right? So we're going to use almost exclusively this sort of method for attacking vector math going forward. So you got to be comfortable doing this vector math. You don't want to be drawing tip to tail forces all the time. All right, it's going to be really annoying. But we did show kind of near the end of class on Friday that if we were to do vector math looking at the forces at this particular particle at A, and you added them all together, you would see that the resultant force that you get in both the x direction and the y direction, both of these guys would be equal to 0. Okay, and since we have this some of the forces equaling 0 in both the x and the y directions, we said that that would be sufficient for this 2D case of equilibrium. All right, so we're going to continue our discussion today now with 2D particle equilibrium, and you're going to learn probably the most important skill that you'll need from this class, and that is the skill of drawing free body diagrams. It's a skill that we're going to practice quite a bit in this class, and if you come away from this class with any skill, hopefully it's the skill to draw really nice free body diagrams. Okay, so we're continuing here now with our discussion on 2D particle equilibrium. And I want to just stop really quick and mention something that I talked about in the very first lecture that I sort of want to reinforce just a little bit for this class. In this class, you'll learn a lot of vocabulary, all right? And you have to be comfortable with the vocabulary in this class to be able to solve problems and move forward in this class. And this even title of this lecture is a good example. When we talk about 2D particle equilibrium, each one of these words has a very specific meaning. And when you look at them, there's more depth to each one of these things than kind of meets the eye. And so you have to know mathematically what each one of these words in English sort of represents if you want to understand what I'm going to lecture about today. So we can break down even each one of these different words that are in the title of this particular slide set to further understand and really get a depth of what does it mean to be in 2D? What does it mean to be a particle, and what does it mean to be in equilibrium, right? So 2D kind of means that we're in like the XY plane. You know, we're concerning ourselves with only the sort of the two normal planar directions at this particular time. When we move on to 3D particle equilibrium, it's pretty obvious that we'll go from just the XY coordinate system to then the XYZ coordinate system. Particle, this is differentiating from, you know, let's say a rigid body. And that particle, right, this is a point mass with no volume. Okay, so that's important that you understand that vocabulary, meaning we're focusing our sort of analysis on just these point masses with no volume. And then equilibrium, we just learned about that at the end of last week, means that the sum of the forces that are acting here are equal to 0. So vocabulary is important. If I write on an exam something like the particle is in equilibrium and you don't know what that means, you're going to be in trouble. Okay, so that's what I'm talking about when if you're trying to analyze a problem and you have to know all the vocabulary. What is equilibrium? What is a particle? What is two-dimensional space? If you don't know what those things are, you're going to have problems. So, you know, I'm just kind of demonstrating that here, but this is kind of the only time I'll really harp on it in this class. But the idea is you need to be comfortable with the vocabulary or you're going to have issues. And I try to do a pretty good job as I move forward defining all the things and the words and the terms that we use so that it's very clear when I use these certain words and these certain terms and the certain vocabulary, what we're actually doing. Okay, so let's move on with our 2D particle equilibrium. And we'll recall here that the basis for all of this is that the sum of the forces is equal to 0 on a particle in XY space. That's really kind of like the breakdown of the vocabulary above. And today we're going to look at this equilibrium, which is a very common situation, and look at how to analyze structures with forces on them that are in equilibrium. If you are sitting on a chair and you are not moving, you're static, you're more or less in equilibrium. And we want to be able to describe, let's say, the force between you and your chair by sort of drawing arrows or drawing forces or drawing vectors to represent that sort of situation. So a situation that exists in the real world that you might want to model using some of your engineering skills, we would call that a space diagram. So let's first introduce that idea. So this is a space diagram. And this is just more or less a sketch or a picture or some sort of physical state that might help you define a problem or that you might want to analyze. So we'll just say like a sketch or picture of a system you want to analyze. Okay. And if you want to do analysis, you're going to want to take what is that space diagram, which has all of these real life things or sketches of real life things that you want to analyze, and break it down into a free body diagram. And a free body diagram, you'll see as FBD for short, is a sort of drawing or sketch of all the forces that are acting on your sort of system of interest. So let's give that a real definition here, and then we'll look at an example. So free body diagram, a lot of times you'll see it as FBD. Okay, and here the free body diagram, we've sort of defined it in your notes. It's a drawing of systems of forces acting on an object or a particle. Acting on a body or particle. Okay, it's usually like a model of a space diagram. So let's put a couple little more pointers on free body diagrams. This is usually a model of a space diagram. Okay. We make these free body diagrams by isolating particular bodies or particles of interest and drawing all the forces that are acting on that one particular particle or body. When we isolate that one particular body, we're said to cut away the rest of the pieces or objects that are acting on that particular particle or body. Okay, so we make this. So made by isolating body or particle of interest. And specifically, what we're going to do is we're going to cut away, quote unquote, sort of all the other members that are in contact with this thing we want to isolate. Okay, so that's the idea. And you're going to cut away these objects and replace them with force vectors. So we then replace cut away entities with forces. Okay, so you're going to get a lot of practice doing this in this course. And I will be pretty explicit about asking for free body diagrams like on exams, on homeworks, etc. So you'll get a lot of practice doing this. And I will grade them harshly. So you gotta make them right. All right. So an example. Here might be something like a space diagram. Usually I try to draw this on the board, but I'm just gonna take right from the notes. Okay, here's an example of a space diagram. You've got these two schlubs here, Rufus and or Doofus, that are hoisting up the crate from the back of this particular truck, and they've got this pulley system sort of set up to hoist the crate from the back of that truck. This is like a real life situation that exists that you might want to analyze. So there's actually people there doing some work on this particular crate. There's a truck chilling on the ground. You've got a system of pulleys, and all this sort of stuff is something you might want to analyze. Okay, so you would transform this particular setup into a free body diagram with some of the techniques that we're about to learn into something that looks like this. So here we're going to isolate the junction at A. Okay, so more or less like this junction at A. And so when we think about like isolating that junction, I'm gonna like draw a circle around that particular point. And you notice that like this circle that I drew, I have sort of like cut through this particular rope. I've cut through this particular rope, and I've cut through the rope down here. And anytime that I sort of like physically cut through an object with my like isolating circle, I'm going to have to draw a force there that represents that I've sort of like cut through that particular object. And so if I'm isolating that particle at A, I'm going to have like three forces that are coming off of point A that are representing like the tension in the wire that is representative and acting in those particular directions. So the free body diagram of this particular situation is going to look something like this. Okay. Where here I've like used TAB as a stand-in for the tension between points A and B in this particular rope. So this is like tension in rope between A and B, okay? And similar idea for tension AC. And here I've got 736 newtons, which I'm assuming is just like the weight of this crate, okay? So the weight of that crate acting downward at point A. This here free body diagram is starting to look like something that you've analyzed on your homeworks or will be analyzed in your homeworks to come. And so we need to go from what is a space diagram that looks like this to a free body diagram that looks like this if we want to do any sort of like engineering analysis. And so this transformation from what's happening in real life to the free body diagram is actually a pretty difficult skill to master. And you'll get a lot of practice with it in this class, and you'll get a lot of practice with it moving forward in some of your other classes as you go through, especially classes like 2002, 2003, 2004, and 3005, and ME363, which is design of machine components. So you got a lot of classes where you're going to be doing a lot of this stuff. So really got to like hone in and master it. All right. Let's look at a couple more examples and free body diagrams that we might construct. Notice here in this particular example, this is a free body diagram of a particle. All right. Specifically, this one junction between all these like ropes at point A. And this is just kind of a particularly interesting point. Maybe there's like a pulley system there that's sort of relaying all the loads on that particular rope, and we care about how much, tension is in the wires at those particular locations. So let's look at some other examples. These free body diagrams don't necessarily need to be on particles, though that's where we're going to sort of start in this class. All right, so some more examples. We just saw free body diagram of a particle. Maybe we'll look at of a body, or maybe an object. All right. So instead of just like this single point now, which is like a particle, we're talking about something that has some volume to it. All right, some larger object. In our space diagram, let's do an example here of this guy. Here might be a space diagram. It's sort of a depiction of something that might be happening in real life. You've got this package rolling on a conveyor belt on its way from the Amazon warehouse to a relative of yours sometime soon over the Christmas holiday. 30 kilograms, they're getting something good, man. Maybe that's a TV. That thing's heavy. All right, so we want to transform this now into a free body diagram. And I'm going to isolate like this crate. All right, so I'm isolating more or less this package. And so I'm going to like draw this whole package as the free body diagram. And to do that, I've sort of got to like cut away the rollers that are sort of on the bottom of this particular object, right? I've also got to keep in mind that there might be this external force that someone is putting on it to push it up these rollers. All right, so I'm going to keep that in there as well. And so a free body diagram, a nice model of this might look something like so. I've still got this force that's acting on it to sort of push it up the rollers that might still exist. And there's a couple of different ways that you might want to model this real life situation. You could potentially just model like one force of the rollers kind of acting at the bottom of this piece. But more realistically, you want to actually include like the force of all three of these particular rollers. I think that's a little bit more accurate. And those are more or less stopping you from like moving through that particular direction. So we're going to just apply 3 little forces here that sort of represent the forces of rollers. Now you might have to make an engineering judgment here to decide whether there's some like friction in the rollers that might be sort of like preventing you from pushing the crate up that particular ramp. That could possibly be true if they're not well oiled. You got some additional friction there. That's also possible. And lastly, this crate is going to have some weight. So we're going to include weight in our free body diagrams as well. So this guy's got some weight, so we can maybe label that as capital W. So I would say this is a pretty solid or a pretty good free body diagram. Usually you want to label each one of these forces. So I might label this as like F1, F2, F3, maybe this is F4 over here, so on and so forth. All right, get the general idea. All right, so that's of an object, or kind of a two-dimensional planar object. We could do a particle in 3D, and we're going to talk more about this sort of next week in the later end of this week. And again, we might have another space diagram. That looks like the following. Some strange sort of like garage door pulley system. It's like backyard engineering. All right, we'll discuss a little bit more about three-dimensional particles in equilibrium. I'm kind of at the back end of this week, but you get a flavor for it now. Hopefully it's a nice appetizer for you. All right. So we've got these two kind of like guy wires that are coming in to touch point A here, and then we've got an additional force P that's sort of pulling this keg off the wall. Let's call this a keg because that's exciting. All right, so you've got the weight of this keg acting as well. And so we might want to investigate what's happening in this particular situation. And free body diagrams in 3 dimensions are a little bit suspicious and hard to draw, but we'll do our best. All right, and you'll, like I said, you'll improve with these as you practice, practice, practice. Practice makes perfect, right? All right, so we got this situation going on here. We've got like the weight of this guy, W, that's acting down. Specifically, I'm like interested in what's going on at the particle here at point A. So I'm more or less just like cutting away all of the things around point A. So I'm going to have to go through this wire. I'm going to have to go through this wire. I still got this force acting, and I got the weight of this like keg acting here. So all these sorts of things I have to add into my free body diagram. So I've got sort of pointing backwards here in 3D space, a little bit hard to draw in 3D, but I've got this tension here, TAC. Sort of acting to the right, I've got this force P. And sort of acting kind of up towards B, I've got here TAB. And it may help if you're working in 3 dimensions to sort of plop a 3-dimensional coordinate system on here so people kind of understand maybe that you're working in 3D. Because without this, it might not be as apparent. So here's like a X, Y, Z. And I think this might make things a little bit more clear. All right. So this would be a good representation of the free body diagram in 3 dimensions. And we're going to do some analysis on figures that look like this kind of at the back end of this week. You can make a cut through like multiple members at once. So this is a multi-cut free body diagram through a truss. Right. One last kind of example for us to look at. So here's our space diagram. Okay, and I've already kind of indicated where I'm going to be cutting through my piece. So here I'm cutting through NN. And after I make my cut, I can sort of choose to either analyze like the right-hand side or the left-hand side. Sort of depends on some of the information that I know in the problem. And we'll sort of discuss this when we get to the trust portion of this class. But let's say that I'm just interested in sort of analyzing the left-hand side of the object here. So I'm going to make a cut and isolate this portion of the body. And so I'm going to have things like, this external force that acts, this external force that acts. And I'm also going to have to consider like the cuts that I made through the physical piece itself and the forces that are associated with the truss at that particular point, right? I might also want to consider like the weights of each one of these members, which I could sort of represent as like, the weights of these guys right in the middle of those members. But let's just say I'm going to neglect weight for now. So I'm going to neglect the weight of the beams for now. And so we might choose to make a free body diagram here that looks something like the following. Sometimes it helps me to draw these sort of like tildes at the location of the cut. So I've known I've like kind of cut through the material. It sort of helps me. I still have these external loads that act. So here's P1. Here's P2. And I'm not going to include P3 because that's not really on the half sketch that I have here. But I do have to include the forces that are associated with cutting through the truss. All right. So I might include a force here that I'll call FBD. Not to be confused with free body diagram. This is the force between points B and points D. Here I might include another force that exists between B and E. And here I'll include a force that exists between C and E. Okay. So this would be a nice free body diagram here for this particular situation. All right. So those are just some general examples. And we'll do a lot of these and you'll get a feel for how to construct them and how to build them over time. So last thing I want to do is we'll do one example today again of particle equilibrium, where we're looking at a space diagram and we'll make a free body diagram from it and do an analysis to sort of learn some information about what's sort of happening. All right. So I'll pull up this example. This is the same example that's in your notes. So if you want to follow along with the notes, that's perfectly fine. And I'll give you a minute to sort of copy this down. Actually, why don't I just copy this directly into the writing pad. Okay, so here we are. We're unloading a ship. Seem to be a lot of dock workers today. 3,500-pound automobile supported by a cable. A rope is tied to the cable at A and pulled in order to center the automobile over its position. Okay. The angle between the cable and the vertical is 2 degrees. We sort of see that in the picture. While the angle between the rope and the horizontal is 30. What is the tension in the rope? All right, so this is a 2D model. And we're going to isolate sort of the particle at A to do this analysis. So I'll give you a second to sort of copy this down. I would encourage you to sort of make a sketch of this, this space diagram as best you can. Okay. So if I wanted to analyze this guy, I would choose to draw a free body diagram of point A. So we've got some information about what's going on there. We know like the angles of the ropes. We've got some information about the weight of the vehicle. So that pointing downwards is going to be something we know. So let's go ahead and isolate the particle at point A. So the circle or the isolation that I sort of want to think of if I was going to do this is making this sort of isolating circle, sort of cutting around point A, where I cut through this rope, I cut through this rope, and I cut through the rope that's just below point A. Maybe I should do it in a different color. So I'm sort of doing this cut right here, right? I could choose to do it a different way. I'll talk about that in just a second, but let's go with this isolating cut for now. Right. So here's my particle at A. All right, so I've cut through, the rope between point A and point B. That's like this rope here. So I can go ahead and include that. Here. And I know the angle that that is making with the vertical is 2 degrees. So I'll also include that information. This is 2 degrees. And we got to give this force a label. Let's label this, I don't know, FAB. And I'll start including my vector labels now. I was getting a little lazy with it. So here's vector FAB. I've got the weight of the vehicle, which is acting down here. This is W.
Professor?
Yes, sir.
Is there an important distinction between using T and F in these free body diagrams? Does it not really matter?
Not right now. We'll talk a little bit more about tension and ropes a little bit later, but for now, not really that important. The question is, for those of you here in person, is there a big distinction between using T or F as the variable? For now, the answer is no. We're just kind of representing a tensile force in this rope this way. All right, and the last one that I need to worry about is sort of like the rope between point A and point C. So I've got this guy kind of coming down at this 30-degree angle. And let's call this the force in the rope here between A and C. And I know that this guy is at an angle of 30 degrees. Okay, so here's my sort of full free body diagram for this particular problem. I've got the weight of the vehicle and the 2 forces that are in the rope. And more or less the question is, what is the force that's in the rope? And so what we're after is, what is the magnitude of the vector FAC? Or for us, I'm going to translate this into engineering language, the magnitude of the force AC. Okay. So we just did a nice homework where we're looking at vector math. So hopefully we're all sort of comfortable with vector math at this point. And we're going to assume in this particular problem that we are in equilibrium. I'll make it pretty clear on the test if that's the case, but here we will assume that. And if we assume equilibrium, you need to know how to translate that vocabulary into math language. If we assume equilibrium, that means the sum of all the forces that are acting at A is equal to 0. Okay. This allows us now to do our sort of 2D static equilibrium, and we can look at summing the forces in the x direction, summing the forces in the y direction. Both of those must equal 0. So let us do that. So sum of the forces in the x direction at A equal to 0, and sum of the forces in the y direction at A equal to 0. It's kind of what we're doing here. Let's do the x direction first. All right. I'm going to go through the resolution of the forces relatively quickly here. So remember, I'm resolving each of these particular forces into components along the x and the y direction using unit vectors. This is something we did last week. So when I think about the various forces here, I've got to resolve this force AB into the x direction through what is the sine of 2 degrees. I've got to resolve FAC into the x direction through the cosine of 30 degrees. Okay, so I'm resolving here and resolving into the x direction with that guy. And I have no component in the x direction for this particular weight. So let's go through that and we'll do that. So in the x direction here, I'll have something like the magnitude of the force AB. That's this guy here. Resolving into the x direction with the sine of 2 degrees. And it's going to be sine 2 degrees. And it's pointed slightly backwards. So this is negative I hat. And I'm going to add to this the magnitude of the force between the man and point A, and resolving that into the x direction with cosine 30 degrees, I hat. Both of these equal to 0. You can sort of drop the I hat at this particular point. And if you want to work through this, you'll get that if you want to sort of solve for this directly, the magnitude of the force AB here is going to be equal to the magnitude of the force AC times cosine 30 degrees over sine of 2 degrees after we sort of settle out our negatives. So we come up with this relationship here that the magnitude of the force AB has to have this general relationship with the magnitude of the force at AC. And here it's going to be something like 24.81 times the magnitude force AC. All right. So the force in the rope AB is about 25 times the force in the rope AC. Sort of makes sense by the picture when you go back up and look at the picture. All right, so that's my x direction. Let's call this like equation star. Now let's do our y direction. All right. Again, here, the sum of the forces in y must also be equal to 0 for equilibrium to hold. And in this situation, you're going to have something like the magnitude of that force AB resolved into the y direction through cosine of 2 degrees. This will be positive j hat. Okay, so if we go back up and look at our picture, here this FAB resolving into the y direction with cosine 2 degrees, generally in the positive y direction. Okay. And I'm going to add to that the contribution from AC. Here it's going to be the sine of 30 degrees pointing downward. Okay. So again, we move up here. We see that this FAC is generally pointed in like the negative y direction. So we're going to resolve with the sine of 30 into the negative j hat. Okay. And I'm going to add to this the weight of the vehicle, which was given to me as 3,500. And this is a negative j hat. All that has to equal 0. Okay, so we're going to want to make a substitution here for FAB is 24.81 times the magnitude of FAC. So let's go ahead and rewrite this guy. So, and we'll drop the J's here. 24.81 times the magnitude FAC times cosine 2 degrees. All right, here I'm dropping the J, so I'm just going to include the negative sign as a minus. So minus magnitude of FAC sine 30 degrees. And again, I'll just include a negative sign here, minus 3,500 pounds equal to 0. There's only one unknown in this equation. That is the magnitude of the force FAC. So you can go ahead and just solve for that if you'd like. So the magnitude of the force FAC here is just going to be 144 pounds after the dust kind of settles. And that really is what we're after here. Okay. So the force in the rope between the man and point A, 144 pounds. You could continue this if you were interested in, let's say, the force of the rope between point A and sort of the top of the crane. So also you could just plug this right back into the substitution that we had before. Which was 24.81 times the magnitude of FAC. And you would find that the magnitude of AB is 3,573 pounds. Okay, so that force AB is kind of doing most of the work here. All right, questions on this problem? Okay, tomorrow we're gonna just do some example problems in class. So I'll bring those with me and share them with you and maybe give you 5 or 10 minutes for each problem to sort of work through it. And then we'll go through a couple examples as a class. So you'll see those come tomorrow. And that's gonna be it for today. So thanks for coming and we'll see you tomorrow.